A very good evening to all. On behalf of the Department of Computer Science and Applications, St. Mary's College Autonomous Thrissur, I warmly welcome our distinguished resource person, all my colleagues, and all the participants to the second day of our 6-day online faculty development program on AI in action, bridging theory and practice in data science and deep learning. Before we move ahead, a gentle reminder to all the participants. Please keep your microphone silent during the session. A minimum of 80% attendance throughout the FDP is mandatory. Participants must secure at least 70% marks in the assessments conducted during the program. All the participants are required to submit the feedback form. The link will be shared at the end of the sessions. Today's first session will focus on a very fundamental and essential area, mathematical foundation for machine learning. As we all know, mathematics is the backbone of machine learning. These mathematical concepts are what make it possible for machines to learn, adapt, and make intelligent decisions. Having a strong foundation in these areas is crucial. We are indeed privileged to have with us an eminent resource person, Dr. Shailesh Sivan, Principal AI Architect, Laennec AI India Private Limited, who will guide us through this fascinating subject. To formally introduce our chief guest, I invite Ms. Manasi Jayasuriya, Assistant Professor, Department of Computer Science and Applications.
It is an absolute honor to introduce our distinguished chief guest, Dr. Shailesh Sivan. Dr. Shailesh is a distinguished academician, AI/ML researcher, and technology evangelist. For the last 4 years, he served as an assistant professor in the Department of Computer Science at Cochin University of Science and Technology, and is currently the principal AI architect at Laennec AI India Private Limited. His professional journey spans several notable roles, including postdoctoral research associate at the Knowledge Media Institute, Open University, UK, research fellow at CUSAT, assistant professor at Sacred Heart College, Tevera, and senior software engineer at various organizations. He holds a PhD in computer science, with his research focusing on computational frameworks for spatio-temporal pattern identification using machine learning techniques. His academic credentials also include an MTech in Computer and Information Science and an MSc in Mathematics. Dr. Shailesh has extensive experience in artificial intelligence, machine learning, deep learning, computer vision, NLP, data science, and even quantum computing. His contribution to the academic and research community are outstanding. Numerous SCI and Scopus Index publications, international conference papers, patents, and book chapters. He is also an active reviewer for reputed journals like Entertainment Computings and has chaired sessions in prestigious conferences. Dr. Shailesh has conducted faculty development programs, hands-on workshops, and webinars across India on trending topics like deep learning, big data, computer vision, and data analytics. His ability to connect research with real-world application makes his sessions truly enriching. Adding to his accolades, Dr. Shailesh has been awarded the Young Scientist Research Award for his exceptional contributions and leadership qualities. Today, as we delve into the topic of mathematical foundation for machine learning, there is no better person to guide us than Dr. Shailesh, whose expertise aligns perfectly with our theme. So I extend a warm welcome to our esteemed chief guest, Dr. Shailesh Sivan. Sir, please.
Thank you, ma'am, for the introduction. So first of all, I would like to thank the organizers and the institution for inviting me and making me as a resource person for this wonderful FDP. And I have gone through the topics and they're all very well aligned. And today we are going to discuss about mathematics for machine learning. That is the very fundamental mathematical aspects that we have learned from the very small classes till the +2 of the graduation. These things are actually getting revised, and the difference is how we are actually connecting these concepts, what we have learned in our classes, with the machine learning techniques. Okay, so we'll be starting with what is artificial intelligence. I know for the last day was enriched with a lot of stuff related to data science, artificial intelligence, machine learning, deep learning, all these stuffs, right? So what is artificial intelligence? Okay, what is the core idea of artificial intelligence? Can someone unmute and tell me what is artificial intelligence? I'm just asking you people for making the session more interactive, because as I'm not seeing you all, I don't know what is happening with you. And if it is in a live session, I can see your face, I can get the response from your face itself. But as we are not seeing each other, I just want to make you engage with an interactive way. So somebody please unmute and tell me what is your idea about artificial intelligence?
Making computers to think like human.
Making a computer think like a human. Yeah. Particularly, if we can start from that point itself. What is your name, ma'am?
Srikala.
Thank you. Thank you for the response. Yeah. So artificial intelligence is particularly a branch of computer science that focuses on infusing intelligence to machines and systems by leveraging data and algorithms, and it enables the system to reason, learn, make decisions, optimize, and even generate creative contents. Okay, so this is the major focus of artificial intelligence, because we are all aware about how we are experiencing artificial intelligence, right? We are all experiencing artificial intelligence through different systems or computing systems, like a mobile phone or a computer or a laptop, whatever it is, whatever computer device it is. The major drawback of a computing system is what it is: a dumb device, right? It cannot work anything by its own. So with that drawback, the scientists from the ancient days itself was thinking about how we can make actually a computer intelligent. Okay, as a result of that, in 1956, the renowned scientist called John McCarthy was actually introduced the word the artificial intelligence as a part of Dartmouth conference happened in London. Okay, so the major focus of artificial intelligence is to make a system think like a human, right? And why we need to make a system think like a human? To make the system enabled with the reasoning, to make decisions, to optimize the process, and to even generate contents. If you look into the current applications of artificial intelligence, like suppose we are considering a surveillance cameras deployed in our road, okay, we can actually detect whether a person is wearing a helmet or not, right? That is a particular example of decision making, right? And we know the artificial intelligence is widely used in scheduling and timetable creation operations, similar to the railway timetables and all. So that is what we are calling as optimization. And the examples of ChatGPT or Gemini, what we are doing is we are actually creating contents from our inputs, right? So to make a system enable with decision making, to perform optimization, and to even generate creative contents, we can actually make use of what? Artificial intelligence. So this is the core idea of artificial intelligence. And what is machine learning particularly? Machine learning. So some people will say machine learning is a subset of artificial intelligence, and some may it can have an intersection. So particularly, the artificial intelligence is actually enabled or realized in different ways We have different strategies in artificial intelligence to make a system intelligent. Okay, and machine learning is actually a particular strategy. Okay, one particular strategy in artificial intelligence to make a system intelligent, right? And the core idea of artificial machine learning is to learn from the past data. And what we are learning a pattern. Okay, we are learning a pattern from the data, and with that pattern, we can actually perform the future predictions. Okay, that is what we are actually doing with machine learning. Okay, so there is a confusion that is there anything other than machine learning in artificial intelligence? What do you think? Can someone say anything other than artificial intelligence in machine learning? Any particular domain or use case or example other than machine learning? Can someone say what is happening in artificial intelligence? Or can we implement artificial intelligence without machine learning? I'm just asking for an opinion. I don't want any answers. Anything other than machine learning within artificial intelligence?
So deep learning, NLP.
Deep learning is again a part of machine learning itself, right? Anything else? NLP? Yeah, NLP can be one example. NLP that uses the traditional language processing techniques. Maybe a grammar checker with NFA or DFA. Or
Data science.
yeah, data science is actually an independent domain that is having an intersection with artificial intelligence. If you see a computer vision technique like face detection can be done without learning. Okay, there are sophisticated mathematical algorithms that we can make use of to detect a face. So there is no need to learn to detect a face. But the thing is, whatever techniques are there within artificial intelligence other than machine learning, they're all limited, they're all not efficient, they're all not robust. Okay. So what we are actually doing is, nowadays we are actually combining the techniques from machine learning with all other subdomains like natural language processing, computer vision, speech systems, expert systems, learning and optimization, robotics. Everywhere we are actually combining the techniques from machine learning to all these domains to make them more efficient and robust. So I can say the 99% of systems, AI systems, now we are experiencing is actually an application of machine learning, or we can say machine learning is somewhat now equivalent to artificial intelligence. Okay, so that is why whenever we are talking about artificial intelligence, we have to mention our machine learning. Okay, so what is actually machine learning? As I suggested or as I defined, machine learning is a technique in artificial intelligence to find the patterns within the data to make that pattern useful for future predictions. Okay, so to apply machine learning for a particular problem, we have to keep in mind that we cannot apply, or we need not to apply machine learning for all the problems. Okay, suppose we are creating a billing software for a supermarket, or suppose we are building a payroll application for an institution or an organization. Do we really need to use machine learning? There is no need to use machine learning, right? So for particularly to use machine learning, we have to choose problems with uncertainty in the relationship. Even within that uncertainty, there should be a hidden pattern in it. Okay, and with the help of machine learning, we must be able to identify that pattern and approximate it into generalization. And with that generalization, we must be able to predict on unseen data with minimum error. Okay, minimum error on unseen data. That is what we are actually focusing in machine learning. Okay, and for every machine learning technique, there are two phases. First one is a learning phase, or a prediction phase, or a training phase, or an inference phase. We can say like that. And according to the task we are performing, machine learning is again divided into supervised and supervised reinforcement learning, right? So if you look into the pipeline of machine learning process, the training part, ML training, machine learning training is nothing but with the help of machine learning algorithms. Okay, with the help of machine learning algorithms, we are extracting the pattern, hidden patterns within the data, and that pattern is expressed as a machine learning model. Okay, machine learning model. Okay, and in the inference part, after getting that model, what will happen? If there is a new data, that data will be applied on this model and you will get the prediction. Are you getting it? Are you getting it? Can you just respond on the chat box? So far, is it clear? Yes. Okay. So, keep in mind, we have machine learning algorithms. That machine learning algorithms will consume the data. Okay. And from that data, the algorithms will identify hidden patterns in it, and that hidden patterns will be expressed as machine learning model. Okay. And in the future, these models will be used for machine learning inference. So there will be a new data, and that new data will be mapped or predicted with the learned models. Okay. So I can simply say one example for this. Okay. A very simple example. See, suppose I have a data like this. Okay. Say I have some XY pairs. Okay. Is it possible to see this?
Yes, sir.
Yeah.
Yes,
So
yes.
I have one data. One is mapped to 1, 2 is mapped to 4, 3 is mapped to 9, 4 is mapped to 16, 5 is mapped to 25. Can you tell me what is the mapping of 10?
100.
Yeah, it's 100, right? Why you are able to tell me it is 100? I have not given you any kind of relationship between X and Y, right? Because your brain is going through the examples I have given to you, and you are able to find a pattern that connects X and Y in a way that the second number is the square of first number, right? So do we really need machine learning for this? That is my question. According to the properties of machine learning problem, we need not to have machine learning for this, because the relationship between X and Y is not uncertain, or there is no uncertainty involved in it. Okay. But if I give you the data like this, okay, if you are getting a data like this, will you be able to tell me what is the mapping of 10? What is the mapping of 10? No, right? Why? Because there is an uncertainty that connects the relationship between X and Y, right? So even in that uncertainty, we cannot exactly say what is Y from X, right? Even in that uncertainty, you will be able to find a pattern here. What is the pattern? Y is not exactly the square of X, but Y is somewhere very nearer to the square of X, right? Here it is 1, it is 4, it is the square is 9, here the square is 16, here the square is 25, right? So if you consider the squares of X, this Y is somewhere very near to that square, right? So that is a hidden pattern. Now what we will do? We will approximate that hidden pattern as Y is equal to, or Y approximately equal to what? X squared. Okay. So here, this is our data. Okay. This is our data. Okay. And observing this data and what we are doing is we will be finding out a pattern from it, right? And this pattern is approximated as a model. Okay, the pattern is approximated as a model. So on getting a new data, what will happen? The output will be mapped to 10 square, that is equal to 100. That is, I can say the output or the mapping of 10 will be 100 with some kind of errors, with a very least error. Are you clear with this? What you mean by an algorithm? What is data? What is model? What is the process of inference and what is the process of training? Is these terms are very clear to you? Perfect. And one more response in the chat. Okay, fine. Now we can move to our core part. Okay. So why mathematics for machine learning? Why we need to have the fundamentals of mathematics for machine learning? Okay. See, at different points in the machine learning journey, we must be able to connect the concepts in machine learning with mathematical theories. Okay. At the very basic, the major component of a machine learning system is the data itself, right? And from the data, with the machine learning algorithm, we are actually getting a machine learning model, right? So, see, from the very basic data itself, data are actually points in Rn. Okay, Rn is nothing but it is a space, mathematical space. It is a mathematical space with real numbers. Okay, a tuple of real numbers, an n tuple of real numbers. And the models we are talking about, can be considered as an operation called transformations in Rn. Okay, transformations in Rn. And the learning optimizes objectives defined via inner products, norms, and decompositions. Okay, so usually while applying a data on a machine learning algorithm, you will be getting a model, right? And that model is actually obtained through machine learning algorithms. Okay, and this algorithm will optimize the prediction error to obtain the model, right? So if you're connecting the mathematical part, this data will be a set of points in a mathematical space called Rn. Okay, and the model we are obtaining from the machine learning algorithm is again a mathematical transformation in Rn. Okay, and to obtain this transformation or model, we are always using algorithms based on different mathematical operations like inner product, norms, and decompositions. Okay, so at the representation perspective, mathematics is very essential for representing the data like vectors, matrices, tensors. Okay, and for different algorithms, we use transformations like linear layers, attention, convolution kind of stuffs. For optimization, we use the mathematical techniques like gradients, Hessians, curvature kind of stuffs. And beyond Euclidean space, we will be using kernels, manifolds, that kind of stuffs for applying on the non-Euclidean data. Okay, and we can actually go through these things in a very detailed way. Okay, and these are the very, very basic techniques we have to keep in mind before learning machine learning algorithms. We know the equation of a line. Okay, equation of a line is represented as ax plus by plus c equal to 0, right? So the one thing you have to keep in mind is if you consider a vector, AB, okay, if you consider a vector AB, okay, that will be always perpendicular to that line. Okay, that will be always perpendicular to that line. Okay, which line? 2x plus 3y minus 4, or ax plus by plus c equal to 4. Okay. And for two-dimensional space, this vector is perpendicular to a line. In the case of three-dimensional space, there will be an equation like ax plus by plus c z plus d equal to 0 that represents a plane, right? The vector ABC will be perpendicular to that plane. And similarly, for any space, for r raised to n itself, for any n-dimensional space itself, if you have a hyperplane represented by n dot v, if you have a hyperplane represented by n dot v, then n will be always perpendicular to that hyperplane. Okay, always perpendicular to that hyperplane. Okay, so what is the idea of this n dot v? It is nothing but, see, if you have an n-dimensional space, a hyperplane will be represented as w1 x1 plus w2 x2 plus etc. up to wn xn is equal to 0, right? And this is nothing but, this is the dot product of the vectors w1, w2 etc. up to wn dot x1, x2 etc. up to xn, right? Now this is a vector w and this is a vector x. So for any hyperplane w dot x, I can say the vector w is perpendicular to what? W dot x. Okay. So in the case of a line, if it is ax plus by plus c equal to 0, the vector AB will be perpendicular to this line. Okay. And if you consider a plane like this, and the plane is ax plus by plus cz plus d equal to 0, the vector ABC will be perpendicular to that plane. And this will be true for any space. Okay, that is what we are representing. If you have a hyperplane w dot x, then the vector w will be perpendicular to w dot x. Okay, hope this is clear for you, right? Okay, and we know what is a function, right? What do you mean by a function? A function is a mapping from one set to another set. Okay, a function is a mapping from one set to another set, and which is having a property that the first set, every element in the first set should have a unique and exactly one element should be mapped to B. Okay, then only it is called as a function. So every element in the first set, every element in A should be mapped to some elements in B. Okay, should be mapped to some element in B, and that mapping should be unique. One element in A cannot be connected to two elements in B. It should be unique. Okay, so in machine learning, we always deal with functions that are called as real. Okay, we are all familiar with real valued function, right? So we are actually familiar with real valued functions, right? What do you mean by real valued function? Real valued functions are nothing but you can take any input as any input, any kind of input, but the output y should be an element of real value, real numbers. Okay, so if you consider a vector as an input, and the function will return the magnitude. The magnitude is a real value, right? So here the input is taken from a vector, but the output is mapped to real. Okay, and if you consider a square matrix and the determinant of that matrix, if the function is mapping to the determinant of that matrix, what will happen? The input is a matrix, but the output is what? A real value, right? And if you consider a complex number x plus iy, and if you consider the modulus of that complex number, it will be x square plus y square, right? That is also a real number, right? So the input can be anything, but the output should be what? Real. That kind of functions are actually called as real valued functions. Okay, real valued function. Okay, that is the codomain should be real. Okay, the codomain should be real. Okay, but there is something called real functions. Real functions are nothing but here both the input and the output are real. Is it clear? Real numbers are nothing but the functions that will take the input as a real number and the output also as a real number. Simply a function f defined from R to R where y is equal to f of x is equal to x square. That is a simple what? A real function. It can also be a real valued function, but this is particularly a real function because both the input and the output are taken from the real numbers. Okay, topic is clear, right? Now, these things are actually very important because tomorrow also we are actually going through the concept of neural networks. There also this concept is very, very important. That is why I'm just going through all these stuff, even though it is basic. Okay. Next, we can move to the limit of a function. Actually, what do you mean by limit of a function? What is the idea of limit? We will always learn about this definition, right? The limit of f of x as x tends to a is a value approached by f of x when x approaches a. Or we require left and right limits to agree. That is, limit x tends to a minus f of x is equal to limit f of x tends to a plus f of x is equal to L. Then we can say there exists a limit. And can we say limit x is for this function? F of x is equal to x less than 3 or f of x is equal to x plus 3 otherwise. Is it possible to say whether the function is having a limit at every point? What is the idea? What is the core idea of a limit? The idea of limit is very simple. It is nothing but, see, suppose we are having a point, we are having a function like this, okay? That is till 2, okay, less than 2, the function is x square, okay? And after that, the function is x plus 2. It is very clear for you, right? Very much clear. Okay. And we have to examine for this function, there exists a limit at 4. Okay, there exists a limit at 4. Okay. So what is the idea? What's the idea of finding there exists a limit at 4? It can be done through an experiment. What we will do is we will take two neighbors of 4. Okay, a left neighbor and a right neighbor. The left neighbor is 3 and the right neighbor is 5. It is clear, right? Then we will evaluate the function's value at the left neighbor and the right neighbor. So at 3, the neighbor's value is 6, and at 5, the neighbor's function value is what? 8. Okay, 6 and 8. Fine. Now, what we are doing is we will update the neighbors towards that 4. That is, 6 is updated as 6.5 and 8 is updated as 7.5. Right? Sorry, 5 is updated as 4.5, 3 is updated as 3.5. Okay, that is from 3 we move to 3.5, from 5 we move to 4.5. Right? Now the function's values are updated as 6.5 and 7.5. Right? Again, we are updating the neighbor towards this 4. Like by taking the interval as 0.1, the value will be 3.9 and 4.1. Now the values are 6.9 and 7.1. Right? On doing this, okay, I am reaching from 3 towards 4 and I'm reaching 5 towards 4, right? From the left-hand side and the right-hand side, on reaching towards 4, what will happen to the function's value? The function's value is actually started from 6 on the left, and it will be updated as 6.5, 6.9, 6.99, 6.999, 6.999, right? So it is converging towards 7. Okay. And from the right side also, we started with 8. It is getting updated as 7.1. From the right side, we are moving towards the left. 7.5, 7.1, 7.01, 7.001, and we are reaching towards 7 here also, right? So from both the left-hand side and the right-hand side, you are converging to a single point, a single value. Then it is called as what? The existence of limit. Okay, that is what we are calling as the existence of limit. So I can say for this function, f of x is equal to x square, less where x less than 2, x plus 3, where x greater than or equal to 2, there exists a limit at x is equal to 4. Okay, is it clear? Right? And see another example. Here, instead of 4, I'm taking the point as 2. Okay, so the left neighbor is 1 and the right neighbor is 3. So starting from 1, I'm reaching towards 2, and starting from 3, I'm again reaching towards 2. Right? So from the left hand side and the right hand side, I am approaching towards 2. Right? But what will happen for the function? If you calculate or if you find the function's value from the left, starting from 1, it is approaching towards 4. It is approaching towards 4. And from the right hand side, starting from 6, it is approaching towards 5. So even if you go, or even if you reduce the value of h into much smaller values, this f of xl will converge to 4 and f of xr will converge to 1. And in that case, the left hand limit and the right hand limit will not converge to a single value, right? At that case, we can say there exists no limit for that function at the point x is equal to 2. Is the concept clear? Is the concept clear? This is a very simple concept.
Yes, sir.
But we will not give much attention towards this concept. But this is very important while learning machine learning. Okay, because we are actually using these concepts at different points while creating machine learning algorithms. Okay, hope it is clear, right? And what is the intuition of continuity? We told that for the existence of a limit, we have to search for, or we have to look for left hand limit and right hand limit. Okay, and this left hand limit and right hand limit are converging to a single value, and that value is same as that of function's value at that point. Then what will happen? We can say the function is continuous. Okay, the function is continuous. Okay, so you may be thinking that that will be true for all functions, right? If the left hand limit and the right hand limit is converging towards a single value, definitely that value will be there for that function, right? You may be thinking in that way, right? So is there any case where we have no continuity but having a limit? Is it possible? I can show you a demo. See, there is a website called Desmos. As you are all teachers, just keep in mind this is a very useful tool for representing the geometrical facts to the students. So see, consider this function y equal to, okay, 1 by modulus of x plus 1. Okay. So what about this function? If you consider, if you look into all other points, there exists a limit, right? But if you consider this point 1, okay, 1 from the left-hand side and the right-hand side, it is converging to a single value, right? And you may be thinking like, so at this point, they have converged to a single value, right? But if you maximize this, or if you zoom it, you can say that even in the infinite value of y, the lines will not converge. But they will be having the same value for left-hand side and the right-hand side, right? Are you getting it? Right? So in this case, the limit is existing, but there is no continuity, because if you just keep a ball rolling through this line, you will go to infinity. You cannot jump from here, jump from this line to this at any point, right? That is why we are saying that it is breaking the continuity. Okay, it is breaking the continuity. Is it clear? The idea of continuity? Okay, fine. Now, the derivative. What is actually derivative? We always say the derivative is actually the slope, right? Derivative is the slope of a particular function. But is the slope really derivative? You should keep in mind, see, slope is calculated like this, right? Change in x by change in y. This is delta x and delta y. And how will you calculate slope? Delta y by delta x. Okay. So this is what we are calling as a slope. But this is actually not the derivative. Okay. This is actually the secant value. Secant. Okay. Or we can say this is difference quotient. Okay. This is called as the difference quotient. When it becomes derivative? It becomes derivative only when you apply the condition of limit. That is, the rate of change of a function at a point, okay, or the rate of change of a slope when we consider the interval x is extremely very small or extremely equal to 0. Then only we can say its function's value is what? Derivative. Okay. Right? That is how we are getting the derivative of x as x square. Sorry, x square as 2x. Because if you calculate the difference quotient at 1, you will be getting the value 2. If you calculate the difference quotient of x square at 2, you will be getting a value 4. If you calculate at 3, you will be getting a value 6. And what is the pattern? This pattern is nothing but this is 2x. That is why we are saying the derivative of x square is what? 2x itself. Okay. So the derivative will give you the idea about, see, suppose, what about the derivative at this point and derivative at this point? A and B. Which derivative will be more? Anybody say, please? The derivative at A or derivative of B will be more? So you're mapping to 3 and 1. What is the derivative of this x square y equal to x square? At 1, the derivative is 2. At 3, the derivative is 6, right? So the derivative at B is more and the derivative at A is less, right? And what is the physical interpretation of that? It is nothing but if you move the neighbors, if you move from B to the neighbors, the change happening on the y will be the change happening on the y will be more than the change happening at a, right? So how much the function will change at a point when you move towards it, towards the neighbors. Okay, that is the idea given by what? Derivative of a function. Hope it is clear, right? The derivative will give you the intuition regarding the change happening on the neighbors of a point for a particular function. So if the derivative is more, you can say the change at that point will be more. If the derivative is small, the change at that point will be small. Okay. And have you ever gone through the function like this? See, what is this function? Y equal to x, right? Y equal to x. And what is the derivative? Dy by dx equal to what? 1, right? Why it is 1? Because the change happening on y from 1 to 2 is 1. And 2 to 3 is again 1. 3 to 4 is again 1. Because the change is constant. That is why this derivative is 1. And if you simply consider this function, y equal to 2. What is the derivative? Dy by dx is calculated as what? 0, right? Why it is 0? Because at 1, the function's value is 2. At 2, the function's value is 2. At 3, the function's value is 2. So whatever value you move on the x direction, the y will not change, right? That is, the change is 0. That is why the derivative is 0. Is it clear? Are you getting the idea? The derivative will give you the intuition regarding the change happening on a function at a particular point. Okay, this is very, very important while dealing with artificial neural network, because this is the base of what we are actually experiencing as ChatGPT. Okay, fine. So I'm moving to the next slide. Now, there are functions which are not having derivative. See, if you consider this function, f dash of x is equal to minus 1 x less than 0, 1 x greater than 0. At this point, you will not be having any kind of derivative. Okay, you will not have any kind of derivative at that point, because its left side difference quotient and the right side difference coefficient will not exist for this particular function at that point 0. Okay. And what is the idea of a multivariate function? So far, we have discussed about functions which are taking one input and one output, right? But if a function is able to take more than one input and give one output, is actually called as multivariate functions. Okay. And a simple example of multivariate function is a bivariate function, where the function can take two inputs x and y, and it will get mapped to z. Okay, it will get mapped to z. Okay, and z is the value of that function. So if you represent that multivariate function, bivariate function here, okay, to represent this, see, you can say its domain is what? What is domain? X can be a real number, y can also be a real number. So the order pair xy will be any point on the plane R close L. That is, its domain will be like this. This will represent any x value, and this will represent any y value. Any point on this surface can be considered as an input towards this function f, right? And if you input this particular point xy into a function f, you will get some z value, right? And you can plot that z value over here. Okay. So for this corresponding xy, you will get a z value. For another xy, you will get another z value. For this, another z value, another z value, another z value. So if you collect all these z values, you can see the function is represented as a surface. That is why one example is given here. Okay. So this is what we are calling as a surface. Okay, 2D surface on a 3-dimensional space. Okay. So every by function can be represented as a 2-dimensional surface. And in the case of trivariate function, we cannot actually visualize it, right? Or in the case of n-variate also, we cannot visualize it. But we will collectively call it as a hypersurface. Okay. What is that? Any n-dimensional function or n-variate function will give us a hypersurface. Okay, will give us a hypersurface. Hope it is clear. And what is the idea of a partial derivative? What do you mean by partial derivative of a function? Why the partial derivatives are important? Partial derivatives are usually represented as dou z by dou x and dou z by dou y, right? And what is the significance of it? The partial derivatives will capture the change of a function towards the x direction as well as towards the y direction. Okay, towards the x direction and the y direction. So suppose for a function, you have a value. Okay, for a function f of xy at x0 y0, you are having a value called 10. Okay, and at x1 y1, you are having a value 20. So what is the total difference happened on the function? 10 units, right? Is it possible to find what is the contribution of x as well as what is the contribution of y towards this 10? Like I can say, like by changing 1 unit of x, by changing the x, you got the difference 8. By changing the y, you got the difference 2. And total, you got a change of 10. Is it possible to tell like that? We can see that. Okay. See, consider a function f of x is equal to z is equal to f of xy, where it is defined as 2x plus 3y. You know what is the partial derivative of z with respect to x, right? It's 2, and partial derivative of z with respect to y, it's 3, right? So at the point 1, 0, what is the value of f? It's 2, right? At 1, 0, it's 2. And what is the value of f at 3, 4? It is 18. So from 1, 0 to 3, 4, the total change happened is what? 18. The total change happened is 18. And you can see on x, how much unit changed? We moved from 1 to 3, right? How much units? 2 units were changed. And on y, we moved from 0 to 4. That is 4 units were changed, right? So delta f, that is the total change 16, can be expressed as delta x into, what is delta x? 2 into 2 plus 4 into 3. So 2 into 2 is 4, 4 into 3 is 12, and this 12 plus 4 is 16, right? So this delta x and delta y changes happened on x and y. And what is this? And what is this 2 and 4? Okay. So the total difference 16 is calculated as delta x into 2 plus delta y into 3. And we know what is delta x and delta y, right? Okay. What is this delta x and delta y? It is nothing but the change in x and change in y. But what is this 2 and 3? This 2 and 3 are nothing but they are the partial derivatives, right? So the total change happening on a function moving from one point to another point is actually contributed by the change in x into partial derivative of x, change in y into partial derivative of that function with respect to y. So if you have the total change, to find out the contribution of each independent variable, what concept will help us? Partial derivatives will help us, right? Then the partial derivatives can be used to find the contribution of change happening on a particular function. Is that clear? This will be applied on a particular algorithm called gradient descent algorithm. Okay, so hope it is clear for you, right? Now we can actually move to these are the fundamental things, and I am now moving to the concept of vectors. So what is vectors? We will be learning about vectors in physics, maths, statistics, everywhere, right? So what is the vector? A vector is nothing but it can be viewed as a point on an n-dimensional space. Okay, vector can be considered as a point on an n-dimensional space. Okay, so it can be represented in different ways, as a column vector, as a tuple, or it can be represented as IQAC representations, or it can be in an angle bracket. The concept is same for a line. Okay, for a line, we have point 1, minus 1. So the magnitude is 1. The direction is either plus or minus. Okay, this plus direction and this is minus direction. For two-dimensional space, if you consider a point 2, 3, 2, 3, so this is a vector, right? So any point on the two-dimensional space can be considered as a vector. So this will be having a magnitude and a particular direction, right? And in the case of a three-dimensional space also, if you consider any point 2, 3, 4, this will be a vector, right? Right? So this concept can be extended into n dimensions. Okay. So any point on an n-dimensional space is actually called as a vector. Okay. And what is the connection between vector and machine learning? How we can actually we can connect the concept of vectors and machine learning. Okay. Here, see, as I said, any point on a mathematical space can be considered as a vector, right? Okay. So a vector space is nothing but it is a collection of such points. It's a collection of such points. Okay. And this is mathematical properties. And the distance between the vectors. Okay. The distance between the vectors, or the magnitude of the vector, is actually calculated through an operation called inner product. Okay. Inner product. If you have two vectors u and v, the inner product will give you what? The distance between these two vectors, right? And it will also tell about the orthogonality property. If you find out the inner product of two vectors, and if it is equal to 0, we can say the vectors are perpendicular to each other. Okay, right? So the inner product will give you the idea about the distance between two vectors, and the geometric meaning of the inner product is it will give you the angle between two vectors. If you find the inner product as mod u into mod v cos theta, the theta will be the angle between two vectors u and v. Okay, and if you calculate inner product with the same vector, it is called as a norm. That norm will give you the magnitude of a vector. Okay, norm will give you the magnitude of a vector. And as I said, the orthogonality, if the inner product are 0, then it is called as orthogonal to each other. And if the vectors are having a magnitude 1, then these vectors are actually called as orthonormal vectors. Okay, so these are the mathematical basis. And we know what is a matrix too, right? Matrix is a rectangular array of numbers that can be represented as a linear transformation. Okay, so if you multiply a vector x, y, z with a matrix like this, you will be getting another vector, right? You will be getting another vector. Okay, so every
Sir,
matrix.
please repeat norm.
Norm. Are you asking about this?
Yes, sir. Sir,
Yeah.
what is its practical significance?
Yeah, the norm will give you the idea of the magnitude of a vector. I have drawn you one in a three-dimensional space. See, yeah, in a three-dimensional space, I said every point, this x, y, z, right, can be a vector, right? So if you calculate norm of this, that is v is v, and norm of v, it will give the magnitude. Is it clear? Is it clear, ma'am?
So norm is actually giving magnitude only.
Yeah.
Suppose we have a vector a plus ib, so we usually compute magnitude like square root of a square plus I.
Yes. That
So how is it different from that?
it is actually same. Actually, if you have ai plus bj, right? That is what you are asking, right?
Yes, sir. Yes.
Yeah. So if you find the norm of this, that is ai plus bj, how will you
Okay.
calculate it?
Okay,
Root
right.
of
A
x
square
square
plus
plus b square. This is same as that of this, right?
right.
Okay, fine. So why we need to bother? I'm telling that every matrix is actually transforming one vector to another vector, right? One vector to another vector. Okay. So that transformation is actually called as a linear transformation if the transformation satisfying these rules. I will show you some example. See, suppose you have a cube. Okay, you have a cube. Okay, and every point on the cube can be represented as 0, 0, 0, 1, 1, 1, like that, right? And see, if you multiply each of the coordinates of the corners with this matrix, okay, with this matrix 2, 0, 0, 2, 1, 0, 0, 0, 1, you can say that the cube is actually elongated towards one side because of the presence of this 2. Okay, it will get elongated towards x. So this particular cube is transformed into this cuboid by applying the transformation 2, 0, 0, 1, 0, 1, 0, 0. Okay, fine. Also, if you multiply a vector x, okay, if you have a vector x, okay, and if you multiply this x with this particular matrix, what will happen? The x will get rotated. Okay, the x will get rotated. The vector will get rotated by 45 degrees. Okay, and similarly, I can say any matrix will transform a vector to another vector by scaling it or rotating it or sharing it. Some kind of transformation will be happening on that particular vector, right? That is, if you have two vectors E1 and E2, that E1 and E2 will be transformed into AE1 and AE2 using some transformation A, right? Okay, that keep in mind. That will be helping us to understand the concept of eigenvalues and eigenvectors. Okay, see, and when it comes to data, these vectors and matrices are very important. Why? Because we often represent a single data point as a vector. See, suppose you are having a machine learning data and the data is represented using features, right? I hope what you know what is a feature, right? So here a student is represented using 3 features: height, weight, and age. And one student, these values, data is represented using 170, 65, and 21, right? I can consider this particular data as a vector. where I can plot it on a three-dimensional space represented by height, age, and weight. So the vector 170, 65, 21 will be a point on the space, right? So if you have such n number of students represented using height, weight, and age, that students will represent a collection of points in R3. Collection of points in R3, right? So if you have a single feature, the single features are represented, example like temperature. You are calculating the temperature of 100 different places. Then it will be a collection like this, right? 30, 32, 28. And it will belongs to R1, right? And if you calculate, see, so if you calculate, or if you collect the data, it's like height and weight, okay? Every data will be having a two tuple, right? A column vector with two values, right? So each of them will be a point on R2, right? And if you have collected the data, height, weight, and age, each of the data will be represented using three values, 170, 65, 21. That will be a point on R3, the space R3, right? And you can extend this idea into n-dimensional space. Okay, you can extend this idea into n-dimensional space, right? If you have n features, x1, x2, etc. up to xn, it will be a point on Rn. Okay, it will be a point on Rn. So, if you have m number of such points, okay, if you have m number of such points, we have m number of such points, and each of this point is represented using n values, I can say each data point with n features can be viewed as a vector in Rn, and the data set with m samples, become a collection of such vectors. That is, the data, every data in machine learning can be considered as a subset of Rn. Okay, hope it is clear for you. Every data we are considering in machine learning can be considered as a subset of Rn with the help of vector representation. This view allows us to apply geometric and algebraic operations in n-dimensional space. Okay, and if you have such a subset, and that subset is actually used to find the different linear combinations using by taking two data x1 and x2. If you're finding a third value, y is equal to alpha x1 plus beta x2, you will get another set of points, and together everything is actually called as data subspace. Okay, that is what we are calling as a data subspace. And in the case of matrix representation, we represent our data as a row. One data with n features as represented as a row, and there will be m such rows. Then I can say the entire data set itself is a member of Rn by n. Okay, the entire data set itself is a member of Rn by n. Okay, so keep in mind, whenever you are thinking about data in machine learning, the data will be either represented as a subset of Rn, or it can be viewed as a matrix in Rn. Okay. See, suppose you have three students as well as 2 as 3, and we collected the height, weight, and age. Then as a matrix, we will represent like this. Okay. See, this is the matrix represent the entire data, and each row will represent the single data point. Hope it is clear, right? And eigenvalues and eigenvectors. See, what is the idea of eigenvalues and eigenvectors? See, we calculate the eigenvalue as a transformation into a vector equal to lambda into v. Okay, a transformation into a vector is equal to a lambda into v. And the values of such lambda is actually called as eigenvalues. Okay, right? Eigenvalues. Okay, so what is the significance? Here A is a transformation and lambda is a constant, right? Suppose you are having a vector. Okay. Suppose you are having a vector 1, 2, 5. And if you choose the lambda as 3 into 1, 2, 5, the vector will be what? 3, 6, 15. Right? 3, 6, 3, 6, 15. So what is the transformation happened on this? Can anyone say what is the transformation happened on this? If you consider 1, 2, 5 as a vector here, this vector 3, 5, 6 will be a vector in the same direction, but it is scaled. Right? It is scaled. Right? So, what is this A? The transformation corresponding to eigenvalues will only scale the vectors, right? Will only scale the vectors. Is that clear? Will only scale the vectors. So what you can think about eigenvalues is the eigenvectors. If you transform any vector with A, okay, any vector with A, it will get rotated or it will get scale or it will get shear or something like that. But the properties of eigenvectors are, if you apply that transformation on eigenvectors, the eigenvectors will only get scaled. It will not change the direction, it will not shear, it will not do any other kind of transformation. It will only get scaled. Okay, eigenvectors will only get scaled. So the eigenvectors will give you the direction in which where vectors can be transformed without any other transformation other than scaling. Okay, hope it is clear, right? And this concept is very much useful for different techniques like singular value decomposition, principal component analysis, or linear discriminant analysis kind of feature detection techniques. Okay, see the principal components. The principal components calculated using the eigenvectors is actually representing the direction in which the variation of the data, is very high. Okay. So, in the case of representations also, data representations also, I said the vectors, matrices, and apart from vectors and matrices, there is something called tensors that can be used to represent what images, videos, and other graph kind of stuff. Okay. So, these tensors are also important. Okay. Then in the case of dimensionality reduction, I will show you one use case how the dimensionality reduction is happening. Okay. So with the dimensionality reduction, we use the concept of eigenvalues and eigenvectors to make it proper reduced vectors without losing the properties. Okay. See, here we have a data. And the data is actually having a spread. And what do you mean by spread? Spread is nothing but how the data is actually changing along each direction. Okay, changing along each direction. See, here you can see if you plot the minimum x value and the maximum x value, the change will be more on x-axis, right? And if you plot the y values, the change will be less. So I can simply say the spread of this data is more on x-axis and the spread is more on y-axis. But if you look into this, the maximum spread can be found in this direction, right? Maximum spread can be found in this direction. This is what we are calling as principal component. Okay, principal component. Okay, first principal component. Next, I can find another direction which is perpendicular to the first spread. This is the second principal component. Likewise, you can again find another vector which is perpendicular to both PC1 and PC2. which is called as the third principal component. Likewise, with principal components, we can actually get the idea of how the data is actually spread over a space. Okay, right? Also, this same concept, that the concept of hyperplanes, we have already talked about hyperplanes, right? Is used in different algorithms related to support vector machine, perceptron, and all. Okay, and again in optimization techniques also we can actually use this. See, we have a rule like, see, if you calculate tangent at a point q, the derivative of a function at q, it is equivalent to the tangent of that particular angle created by this vector. Okay, tangent line. So suppose this magenta line is creating an angle theta q, then tan theta q is equal to what? Derivative at q. And tan theta p is equal to derivative at p. And obviously we know that here tan theta p is less than tan theta q, right? Tan theta p is less than tan theta q. Sorry, theta p is less than theta q, then tan theta p is less than tan theta q. So definitely the derivative at p is less than derivative at q. So moving towards this m, what will happen? Moving towards this m, the angle becomes 0, right? The angle becomes 0, theta m becomes 0, then tan theta m equal to 0. And the derivative will also become 0. So what is the peculiarity of this point? This is a point where we get the derivative as 0, right? And these points are actually called as extremum points. Okay, extremum points. So how can we find that extremum point? Can you think in the reverse way? To find the extremum point, we have to find the derivative, equate it to 0. After that, what will happen? If you equate it to 0, then you will get a point where satisfying that equation, right? Then that point will be the extremum point. Okay, so this is applied on a single variate function. This can be applied on a multivariate function too. Okay, as I said, if you consider a multivariate function, okay, if you consider a multivariate function, the partial derivatives, okay, the partial derivatives, see, suppose we are having a multivariate function like this. We are having a function like this. Okay, this is a plot of a function. Is it equal to f of xy? Okay, the partial derivative will represent a tangent across, a tangent in the direction of x-axis, that is dou z by dou x, and this tangent is represented by dou z by dou y, right? So at the extremum point, what will happen? All these tangents become parallel, right? Parallel to the planes. Okay, parallel to the planes. Then all these derivatives become 0. All these derivatives become 0. And if you consider an n-dimensional function, you will be having the partial derivative with respect to x1, the partial derivative with respect to x2, etc. up to partial derivative with respect to xn, right? And this collection of partial derivatives are actually called as what? Gradient of f. Partial derivatives are called as gradient of f. So to get the optimum point, what should happen? What is the key? All these partial derivatives should be 0. That is, this must be equal to 0, right? So how can we find the optimum point in a multivariate setup? Simply find the gradient, equate it to 0, then you can able to find the extremum point for that function, right? See, that is a very simple technique, and this simple technique is actually the key of all the neural network algorithms, and that is named as gradient descent algorithm. We are actually discussing that part in the tomorrow session. Okay, so hope it is clear for you why gradients are important. Okay, and again see, this is the idea, that is if you're having a multivariate error surface, you will be starting from a random point and towards the inverse direction of gradient of a function, towards the inverse direction of a gradient of a function, we will be moving, and at a particular point, we will arrive at the extremum point. That can be minimum or maximum, right? This is the core idea of gradient descent. Okay, so we can actually discuss this in a very detailed way tomorrow. And here, the concept used is gradient. That is what I want to convey to you. What is a gradient? Gradient is nothing but it is a vector represented by the collection of partial derivatives. And if you move in the negative direction of that gradient, you can arrive at the extremum points. That is the key idea, right? And this is a case study how the PCA works, how PCA can be implemented in an algorithmic way. So the steps in PCA is nothing but, suppose you are having a data X, okay? First, you have to translate that data into the center. That is what we are doing here, center data. For that, what we are doing is we will simply subtract the mean of the data from all the data points. The mean of the data from all the data points. So it will get centered, okay? Right? It will get centered. Then we will calculate the covariance matrix. That covariance matrix is used as the baseline, and with that covariance matrix, you will find out the eigen values and eigenvectors. And after getting the eigenvectors, you can project our data into that eigenvectors to get the reduced coordinates. Okay, so the steps are having the data, we are centering it, we are finding the covariance, selecting the eigenvectors and projecting on it. This is a simple algorithm. Okay, and I can show you one visualization. See, this will make it more clear for you. First, we have the data like this. Okay. First, we have the data like this. Okay. Now, on the second step, what we will do is we will center the data. This data will get centered into the origin. For that purpose, what we are doing is we will simply subtract the mean value from all the data points. Okay. So you will get the data centered. After centering the data, you will find the eigenvectors. See, these are the eigenvectors. This one, and this one. 3 eigenvectors will be found, and this is what we are calling as principal component. That red is the first principal component. This is the second principal component, and this is the third principal component. Okay. After finding out the principal components, you can see that the spread of the data is actually captured using this principal eigenvectors. Okay. That is, the variance of the data is more towards the direction of red, then towards this violet, and then towards this brown. Okay. So this is the first principal component. So what we will do is, if we have a vector, we will project all the data into that. Okay, we will project all the data into that. Then you will get a single value to represent all the data. That is the first principal component values for our data. Suppose you want to get two reduced values, what we will do is, you will take the first principal component and the second principal component. You can consider a plane that constituted by these two vectors. Then you will project all the data into that plane. That is what represented here. First principal component and second principal component. You will get a plane, and all the data is projected to that plane. Then every data is now represented using two values. That projection is represented here, right? So in the three dimension, the data is represented using three values, but after projecting it into two, every data will be having only two components. Okay, so this is how the principal component algorithm works. And remember, for all these things, we have used the very mathematical foundations. Okay, the shifting, the transformation, the eigenvalues, the eigenvectors. So if you learn mathematical in this way, the another perspective of machine learning can be unveiled, and that will make you that will help you to understand these concepts of algorithms and the data in a very beautiful way. Okay, and apart from this, higher concepts in mathematics like manifold Riemann techniques are there for the higher machine learning techniques. But I think for the understanding of the sessions, upcoming sessions, these foundations are very much important, and it will be helpful for you. So thank you. So
As we come to the close of this enlightening session, it is my privilege to extend a heartfelt thanks to our esteemed resource person, Dr. Shailesh Sivan, for sharing his deep insights on the topic Mathematical Foundation for Machine Learning. Your clear explanations and rich expertise have truly deepened our understanding of the mathematical concepts. We are grateful for your valuable time and thoughtful guidance. Thank you very much, sir.
thank you.
Thank you all for staying actively engaged. We truly appreciate your enthusiasm and contributions. Thank you.